Get going with our last speaker, certainly not the least, Professor E.H. Yan of Department of Mechanical Engineering. The title of his talk is Atomically Thin Magnetic Crystals Towards Emerging Spintronics and Quantum Information Science. E.H., you're on.
Okay, everyone hear me?
Yeah, we hear you.
All right. So I'm gonna introduce today atomically thin magnetic crystals that we have been developing here, and this new type of magnetic 2D semiconducting materials are important candidates for emerging spintronics and quantum information science in the future. So what we do here is to develop this synthesis of 2D dilute magnetic semiconductors in which semiconducting properties and ferromagnetism coexist. Okay, so in order to develop these materials, what we do here is to in situ dope transition metal atoms into transition metal oxide, transition metal dicarboxyl monolayers, and that will enable ferromagnetism with a Curie temperature above room temperature, which we demonstrated, which is also practically very important for any practical applications. All right. Somehow it is frozen. Okay, so let me try it this way. Okay, so the journal Science suggested questions that point to critical knowledge gaps, and the ground rules scientists should have a good shot at answering the questions over the next 25 years, or they should at least know how to go about answering them. And they ended up with creating 125 questions, and which was the fitting number for Science's 125th anniversary. So among those 125 questions, one major question was about the magnetic semiconductors, especially the magnetic semiconductors that work at room temperature, because otherwise any materials would not be warm enough for spintronics or any other practical applications. All right. Something is not right here. Okay, I don't know what's going on here. Let me see. Okay. Hope this works better. So let's turn our attention to graphene and other 2D semiconductors. In 2004, Gaiman and Novoselov discovered graphene, resulting in the award of the Nobel Prize for Physics in 2010. And one problem with the graphene is gapless semiconductor. So basically, you cannot use this material directly into electronics and optics. On the other hand, some of other 2D materials, such as transition metal dicarboxyl, when they're thinned down to monolayers, they show a direct band gap, which means that they're direct semiconductor and direct band gap semiconductor, and that means they can be directly used in electronics and optics, complement graphene. All right. So these 2D materials largely decouple from substrates, allow electrical control, and are flexible and are open to chemical functionalization. Let's imagine that we induce this ferromagnetism in these 2D crystals, or these 2D crystals have intrinsic properties of this ferromagnetism. Then combined with their already rich properties in optics and electronics, this could lead to new ways of doing all these computing and communication. All right. However, there was no reported magnetism in these 2D materials until 2017, when the first observation of the ferromagnetism was reported. And these materials were either either insulator or conductor. And these ferromagnetism was shown only at the cryogenic temperature. And these materials were, formed using exfoliation, using Scotch tape, basically not scalable, and some of them were unstable in air. So a lot of questions, a lot of improvements to have here. Nevertheless, there's enormous room to engineer 2D magnets for electronic and photonic materials, which could be transformed into these applications, including low power spintronics and quantum computing applications in the future. All right. So there have been several review articles published very recently, like 2019 and so on, in Nature and Science on the magnetism in two-dimensional van der Waals materials. And this specific review article specifically lists the potential research topics for magnetic van der Waals material. First in that list was a room temperature ferromagnetic material. So that's exactly what we do here. The same year, this was magnetic 2D materials review article by Novosel, the Nobel laureate, and 2019 published in Science on two-dimensional magnetic crystal. All these review articles say as soon as 2D magnetic materials can be reliably synthesized with sufficiently high critical temperatures, the potential for the technological impact to the society would be enormous. All right. So here we can catch two keywords here. Reliable synthesis and high critical temperatures. I want to add one more, semiconducting property. So if you have these, in addition to these two, you have semiconducting properties. Basically, you can directly use this directly combine or integrate this into existing semiconducting devices and so on. So to the semiconductor and Curie temperature above room temperature, or at least at room temperature, and the potential scalability, especially uniformly in terms of doping these materials so that you have these uniform magnetic properties here and there, right? Not just here. So we have successfully synthesized a magnetic semiconductor whereby a molybdenum sulfide crystal is substitutionally doped with isolated iron atoms, creating a transparent and flexible magnetic material only 2 atom thick. And these material works, of course, work at room temperature. Therefore, we can directly integrate this into well-established semiconductor technology. So to synthesize material, we rely on the reaction of transition metal oxide and chalcogen powder in a vapor phase. And specifically for molybdenum sulfide growth, the initial reaction between the transition metal oxide and the chalcogen atoms produces intermediate volatile suboxide, which then through the further sulfurization, it will make the complete conversion into molybdenum sulfide grains, creating these monolayers and bilayers based on your target. So in order to dope irons into this crystal, we use iron oxide particles cast onto the substrate, which then contacts onto another substrate face to face with the molybdenum oxide deposited. Okay, so this is the transition metal oxide, which will be used to convert into moly disulfide. Then with the right temperature, right time, putting right carrier gases and chalcogen powders, and then we held the furnace at the right temperature, right time before it is cooled down to the room temperature where iron doped molybdenum sulfide monolayers are obtained, and we make this into up to a millimeter size, which is significant in this area here. So for example, in the figure A here, the large area growth is important. So first we start with growing single crystal monolayer, isolated one, as shown in this A on the top left. Then further grow will have this merged layers. Eventually you get this continuous film, basically a continuous monolayer with all these iron dope. Okay, and this is collaborative work, and so we do this synthesis, but for characterization we send our samples to various labs. Okay, so that's what we do here. So it is also important to confirm the substitutional doping. And if you have interstitial doping or you have adhesion of these nano particles of these ions, basically it's not going to work when you fabricate devices, right? So it is important that you have the substitutional doping. We confirm this using contrast corrected STEM images of iron doped molybdenum sulfide as well as tungsten sulfide here. Basically what we do here is to compare the intensity spectra based on those atomic numbers and so on. And basically we can very precisely determine doping site. And so, of course, we have also performed other measurements in addition to this, which I don't show here. And also it is important to show and confirm the magnetic field from the material locally as well as globally. Globally means the average magnetic field. Local is important because we have to confirm that this magnetism comes from these doped atoms, right? So we for the local magnetic field measurement, we used optically detected magnetic resonance spectra of the nitrogen Baker center, which are basically nano diamonds with defects and spun onto the sample. And you measure this increase of Zeeman splitting, as you can see from these blue dot there are points, and that indicates the presence of local magnetic field. All right. For the average magnetic field, we use a superconducting quantum interference device measurement, and that shows the pronounced magnetic hysteresis loop, and which of course decreases with increasing temperature, while the Curie temperature has not been reached at room temperature. Okay, so we have confirmed these the material is magnetized all the way up to the room temperature here. So in summary, we enabled the direct synthesis of in-situ iron doped molybdenum sulfide as well as tungsten sulfide monolayers, and we overcome all these difficulties of previously reported results like post-processing and scalability issues and so on. And also we realized room temperature ferromagnetism from the iron doped molybdenum sulfide, and iron doped tungsten sulfide doesn't show any ferromagnetism. So that's an area of research that's something that we are working on now. Anyway, because of this device is these materials is room temperature material. There's this is toward practical 2D spintronics applications in the future, as predicted by theory work. So as a perspective, this magnetic field strength in this material is 0.5 millitesla at room temperature, and this magnetic field strength is quite weak, so it doesn't allow us to pick up a paper clip. However, it is large enough to alter the spin of electrons, which means that these materials can be used to construct transistors to control the spins of electrons while the whole device remains lightweight, flexible, and transparent. So that means this work could lead to a new information technologies with exciting applications in computing, sensing, and data storage. Okay, so I kind of flew through. Okay, so this is it. Thank you.
Thanks much, EH. Exciting work. For some reason, I couldn't open the Q&A box. EH, can you do it? Maybe because of the screen share.
Okay, I have one. Enjoyed your speech. I have what are the main application of iron doped materials? Oh, okay. So what are the main applications? So iron doping, you can dope anything, not just irons, but iron is one of the materials that through the theory work that achieve room temperature ferromagnetism. Basically, we make this material, this is a 2D semiconductors, and then basically what we turn this material into is a 2D semiconductor with ferromagnetic property, and that shows at the room temperature. And it is extremely important because if it shows all the properties, but it is all cryogenics, then basically it's useless, right, in a practicality point of view. But we showed that for the first time, we show that this is room temperature materials, and scrutinize all over the, atom by atom and all the areas. So that's what we did. And this can be used in the future for quantum computing, and it can, for example, Shulman just to talk about this quantum qubit, and this could be used as a quantum dots, dilute magnetic semiconductor quantum dots and qubits and so on, and magnums, and of course for spintronics, any fixed layers and free layers, and so basically this would be useful for future technologies.
Okay, thanks, EH. We are only 5 minutes away from the school's faculty forum. This concludes the forum today. I thank our wonderful speakers for their enlightening presentation.